So this is 12.2, number 37, and the key here is to represent the forces involved in the problem in 2 dimensions by using vectors with 2 components. So I've got 2 force vectors pointing in the direction of each of the ropes. I'll call them U and V, and then I have a force acting on the object which goes directly downward. So I'm going to draw these things in a plane, and I'm going to do my best to sort of represent them component-wise. The problem is I don't know the length of U and the length of V. The 2 and the 3 are meters, and those are not indicating the magnitude of force, so don't let that trick you. Okay, so the W vector is pointing directly downward in 2 dimension. That would give me components 0 and then the magnitude of force there, which is 350. So 0, negative 350 would be the components of the W vector. Now for U and V, again, I don't know how long they are, so I need to write their components just in terms of those unknown lengths. So if I draw some triangles involving the angles involved, I can use trigonometry to help me get the components. So here's the triangle for the U vector. I've got an angle of 50, and the length of the hypotenuse is that unknown length of U. So using trigonometry, I see that the magnitude of the x-coordinate should be the magnitude of U cosine theta, which is 50 in this case, and then the vertical component is going to be magnitude of U sine of 50. Of course, U points into the second quadrant in the plane, so I'll just draw some x and y axes here to help see that. So its x-coordinate must be negative, and I know its magnitude from the trigonometry I did below. So here's the x-coordinate, negative magnitude U cosine 50, and the y-coordinate is the positive value that I got from the triangle. I'll do the same thing for the V vector here. Both the x component and the y component are positive because V points into the first quadrant. And once I get that set up, I will have coordinates for all 3 vectors, W, U, and V. And of course, the key idea here is that since the object is balanced, it's not moving anywhere, all these vectors must add up to 0, basically. So the force that U and V put together should counterbalance the W. And that's a principle that's used in pretty much all these like force balancing problems. If the object that these forces are acting on is not in motion, then they all add up to 0. So knowing this will help us figure out those unknown quantities for magnitude U and magnitude V. If I set up the equation that I get from equating the x-coordinates and y-coordinates of these 3 vectors, or sorry, like adding up the x-coordinates equaling 0 and adding up the y-coordinates equal to 0, then I just have like a linear system that I need to solve in terms of magnitude U and magnitude V. So that should get you started and just solve for magnitude U, magnitude V. So this problem is very similar. This is number 40 from 12.2. Again, the key is just to get these vectors represented in a convenient way in the 3-dimensional system this time. So I'm going to choose to put the first vector along the x-axis just because that makes its coordinates really easy. So since it has magnitude 25, I see putting it along the x-axis is going to give it coordinates 25, 0, 0. Now V is at an angle of 100 from the first one, so I'm going to draw an xy plane just to help get a visual there. Its length is 12, and I can use some trigonometry to help me get the coordinates now of the V vector. And I have to understand that both of these vectors are in the xy plane. That's how I'm setting it up. And so when I go back to 3 dimensions, I'm going to give them the appropriate 3 coordinates with U and V both having a z coordinate of 0. Okay, so here goes a reference triangle. I'll put a 10-degree angle here. This is just helping me get that negative x coordinate and positive y coordinate for the V vector. And then I'll take those values and transfer them over to the 3-dimensional context. So it's a little bit awkward here that the sign is going with the x-coordinate, but that's just how the triangle is set up. And then I move on to the last vector, which it's supposed to be perpendicular to the plane that U and V are in, but that's the xy plane, which is very convenient because that puts the last vector just right along the z-axis with coordinates 0, 0, 4, since its magnitude is 4. So the same principle as last time. I want to find a counterbalancing vector. Really, I just need to figure out how long it is. So what I know is that U plus V plus W should, plus this unknown 1 vector should add up to the 0 vector. And with that, I understand that the magnitude of t should be the same as the magnitude of u plus v plus w. So go ahead and add u and v and w together and get the magnitude as the answer. Okay, for the last problem, this is number 46 and 12.1. The key idea here is that you've got two spheres that have equal radii. Their radii are both length 2. And if you notice, after putting the spheres in standard form, their centers are 3 units away. So I'm just drawing even just like a cross-sectional picture of that situation. And what's going to be really helpful is if you notice that I'll mark some red distances here, this distance, and this distance. Try and figure out what they are, and they'll help us solve the problem later. So this is sort of the situation between the spheres. They are bounding this three-dimensional object. I'll do my best to sketch it over here, but it's like having two spherical caps glued together. So it's like having like two contact lenses glued together. And so how do I find the volume of this thing? Well, it is symmetric, so let me just figure out how to find the volume of one of those spherical caps. You can Google it and see how it's computed, but I'll go ahead and show you how it works. You can set it up as a volume of rotation from Calc 2. So think about, remind yourself how volume of rotations work. There's just an integral formula that helps you compute those things. The issue is that you need to position that spherical cap in a convenient way to set it up. So I've put like one of the spheres centered at the origin in the XY plane. Use the sketch above with those red distances to help you figure out what that blue starting point of the volume of rotation is. So once you figure that number out, what you're going to do is you're going to integrate from that blue number up to the number 2, revolving the function around the x-axis. So the formula is pi r squared, basically, where r is the distance from the x-axis to the function. So if you figure out what that function is in terms of y equals f of x, then you just place it in there and compute the basic integral that results.